Hi everyone, in this video I'm going to talk about using target boost modes with modular ECUs. So first of all, let's talk about the reason why we do it this way. What we found with the select ECUs was that the majority of people were happy just to run an open loop boost control system where you just specify the duty cycle and that's about it. But then we found that in a lot of cases people wanted to run different duty cycle or different boost levels under different conditions, such as different gears, different ethanol content, a switch operated by the driver and that sort of thing. Now, complicating things further is that a lot of people wanted to run closed loop boost. So if you're going to have all these different corrections and conditions giving you different duty cycles, you need to have different closed loop boost targets as well as the different duty cycles. So what it meant in practice was that there's two separate things that you need to tune for each one, which people never kept up to date, and it was a bit of a complicated system basically. It also got a little bit harder when people want to run, say, a lower duty cycle for ethanol or in a lower gear or something like that, but the lower duty cycle doesn't actually correspond to a constant boost curve. You either have boost creep or boost taper depending on the limits of your exhaust or wastegate system, and that also made it a little bit not ideal. So with the modular ECUs we've gone away from that. So instead of having separate duty cycles that you have to enter and a separate target that you have to enter, what we've done now is there are two separate ways of running the boost control in the ECU. One of them is open loop, where you just have duty cycles which can be limited by gear, ethanol content and an input switch, and you can map that against throttle position and RPM. And the other way is the target boost mode, and we've got two different target boost modes. Most of the calculations are the same between both, so I'll treat them as one. And what that means is that instead of entering the duty cycle in all these settings and maps, you actually enter the boost that you want. Then there's a separate table which allows the ECU to calculate the required duty cycle from the target boost, and it uses the same target boost as part of the PID for closed loop control. So in all the settings, for example, the basic boost table or the limits against ethanol, gear or digital input switch, these values stop being duty cycle values and are now your target manifold pressure. So if you read map in kPa, then it's an absolute pressure. And if you like PSI in inches of mercury, then the values, they're displayed as a gauge pressure, but it's actually calculated internally as an absolute pressure. So firstly, the ECU calculates the target map using exactly the same algorithm that it would have used on an open loop system to calculate the open loop duty cycle. So all the limits are applied just the same as in the other system, and if you're not familiar with how that works, then you can look at the open loop duty cycle video or article. So then that new target map becomes the target for the closed loop PID control, and the ECU also needs to work out the open loop duty cycle, the starting point if you like, from that target map. Now there are two ways to do this. The first way is with the duty cycle map. So in this case you have target map on one axis, RPM on the other axis, and the values in the cell are the duty cycle that you need to achieve that boost level at that RPM point. So that's probably the most straightforward way from the ECU's point of view, and from the tuner's point of view that gives you the most control. But on the other hand, it is quite fiddly to set up. So the second way you can do it is using an actual boost map, where the axes on the map instead are RPM and duty cycle, and then the cells in the map are actually the manifold pressure that you get, boost if you like, or map, under that duty cycle and RPM combination. So then the ECU, when it knows that it wants a certain target map, it looks through the column that corresponds to the current RPM, it interpolates obviously, and then works out what the duty cycle needs to be based on where it falls within that table. So you can consider that to be reverse interpolation if you like. Now what it means is that all you need to do is lock the duty cycle to each of those rows of the table in turn, and then get the ECU to learn the boost that you get under each duty cycle value at each different RPM. And once you've done that, then your table's filled out. You don't need to sit there and adjust everything. Now after the ECU has the base duty cycle, which it's interpolated or reverse interpolated from one of those two tables depending on which mode you've got selected, the air temperature compensation duty cycle is applied. So this is still the duty cycle table, but the vertical axis now is the target map rather than the measured map. Yes, it means you can't do your semi-closed loop thing, but you've got a real closed loop controller there to do that, so that's no great loss. What it means is that based on the target map you may find you need more correction at higher map levels for air temperature than at lower map levels. I mean, ideally, if the mechanical system's set up well, you shouldn't really need any, but the tables are there for some cars that do need it. They're there in some factory ECUs as well, so that tells you that there's a real effect. Okay, so now we've got the duty cycle and the target map, so let's look at the other conditions that the ECU needs. First of all, you still have the minimum throttle position, minimum manifold pressure requirements, the same as in open loop mode, so they still have to be met for the wastegate output to be driven. Otherwise it'll just be at 0%. Secondly, there's a quick spool option. So This holds the gate open, or the actuator open, at 100% until it gets within a certain bandwidth of the target boost. So for example, if you're aiming for 15 psi boost and you've set that, that window to 3 psi, then as long as you're under 12 psi, but the other conditions of throttle position and map have been met, then the output will be locked at 100%. And the idea with this is to help spool the turbo more quickly. Now, if the mechanical system is set up well, then the wastegate should be fully shut under these conditions anyway, so it shouldn't make any difference at all. But again, on some cars it does seem to help, so the option's there for people that want to use it. Now, after it goes out of the quick spool function, there's a time delay before the ECU will enter closed loop control. The point of this is to avoid the integrator wind-up problem that happens if you start your closed loop control too early. It'll just create oscillations, which leads to overshoot and, leads to suffering and so on. So then the next point you have is the PID gains. So if you want to just run open loop, then you'd leave these all set to 0. And they're in units of percent either per second or times second, depending on whether it's integral or derivative. So in other words, if your target is 210 kPa and you're actually at 200 kPa and you enter in a gain of proportional gain of 100%, then the ECU will add 10% onto your wastegate duty cycle value. Now in practice, that's a lot to make such a small change. So in practice, you're not going to run gains anywhere near 100%. They're going to be much lower than that. So my advice is to work up from 0. And the other thing is, of course, the maximum percentage correction allowed. That's an amount that the ECU is allowed to move away from the base duty cycle value from the closed loop control. So again, having smaller numbers here, it's just like the closed loop fuel control. Smaller numbers are more forgiving of setup problems. Larger numbers are more forgiving of systematic mechanical problems, and the ECU's ability to compensate for them. But in general, the idea would be to set up the system properly in the first place, so you don't need to do a lot of closed loop correction to fix it. Now finally, just in terms of diagnostics, it's similar to fuel control. So the idea is that you want to have it working properly in open loop control before you go and enable the closed loop control. Once you enable the closed loop control, work up from low values. Like I said, 100% will be way too much, so I'd start say 5%, 10%, that sort of thing. Any integral term you have will actually be a potential source for integrator wind-up problems, especially if your map isn't very good. So I'd say try to do as much as possible with the proportional and derivative terms. That several aftermarket boost controllers don't actually run an integral term at all, they only do proportional and derivative for this very reason. So if you can get the most done with the proportional control, then that'll get you in the best sort of position. Thank you very much.